Presented live from a chaotic and perpetually destructive universe that seems eager to spit in the face of even its most spirited individuals, this is Physics 122. We will encounter scenarios where we have a circuit that contains many batteries and resistors, and very often we will want to describe the behavior of that complicated circuit as being identical to a simple circuit that contains a single battery and a single resistor. So, for example, we might have a very unappealing circuit with many batteries and resistors that are all connected in complicated ways to each other, but we would like to determine an equivalent circuit that contains one battery and one equivalent resistor. So how can we go about transforming from this giant mess on the left to the much more appealing circuit on the right? The way we are going to do this is we will look for certain patterns in the way that the circuit elements are connected to each other. One way that circuit elements can be arranged is known as series. When circuit elements are combined in series, they will essentially be lined up with wires between the circuit elements. Here's a picture of some resistors that are connected in series with each other. You could imagine that current will flow out of the battery through the first resistor, then through the second resistor, and so on through all the resistors that are connected in series. Whatever current flows through the first resistor must be the same as the current that flows through all the other resistors in series. The reason for this was discussed in a previous video. We do not want charge building up at any one location in our circuit. These resistors that are connected in series can be said to be equivalent to a single resistor whose resistance is given as the sum of all the individual resistances of the resistors that are connected in series. So I could say R equivalent in series is equal to R1 plus R2 plus R3 and so on for however many resistors are connected in series. Another way that you could arrange circuit elements is known as parallel. Here's a picture of some resistors that are connected in parallel. You may imagine that current will flow from a battery through a wire and then that current reaches a junction. That current will be split and divided to flow through resistors R1, R2, and all the other resistors that are in parallel with each other. Because of the conservation of charge, the total current flowing through all the resistors in parallel must be equal to the current that was flowing through the wire before the current split. The resistors that are in parallel with each other can be said to behave identically to a single resistor whose equivalent resistance is given by this equation. Notice that the right-hand side of this equation is the sum of the reciprocals of the resistances, and that gives me 1 over R equivalent. When we are solving a circuit problem, we will want to know R equivalent. That means that after I have calculated the right-hand side of this equation, I will need to invert that result to give me R equivalent itself. In lecture, we said that if you have a group of resistors that are in series with each other, then those resistors in series will behave identically to a single resistor whose resistance is given as the sum of the resistances of those resistors in series. Here I drew a picture of two circuits. On the left, we have a circuit containing a battery of voltage V and 3 resistors that are in series, labeled R1, R2, and R3. On the right, we have a battery of the same voltage V, and that battery is connected to a single resistor, which I call R equivalent in series. In lecture, we claimed that R equivalent in series would be the sum of the resistances, in this case R1 plus R2 plus R3, but we did not prove that claim. I also labeled points A and B in the circuit. A and B are just locations in the circuit that I will reference later on in this derivation. Here we will derive the equivalent resistance of 3 resistors in series. The equivalent resistance of any other number of resistors in series can be demonstrated with a method very similar to what we do here. One of the key points in our derivation is going to be to recognize that the voltage drop from points A to B will be the same in both circuits. The reason for that is in both circuits, point A is directly connected to the positive terminal of a battery, and in both circuits, point B is directly connected to a negative terminal of a battery, and we are assuming that the batteries in the two circuits are identical, namely they have the same voltage V. Previously, we described a battery as a type of device that maintains a constant potential difference between its two terminals. So the voltage drop from point A to B must be the same in both cases. Now let's pause for a moment and think about what do we mean by an equivalent resistor? One way of thinking about this question is to say that we want the behavior of the circuit to be identical in both cases except for the locations of the resistors. So some stuff will be happening in these resistors, something will be happening in this equivalent resistor, but for the rest of the circuit, the behavior should be identical. One way I could think about this idea is if I were to cover up the resistors in this problem, then you should not be able to tell me which circuit has 3 resistors and which circuit has 1 resistor. The behavior of everything else going on in my circuit is going to be identical in both cases. Now there's not much else in this circuit, there is just a battery, but there will still be a current flowing through that battery. So I expect the current flowing through the batteries should be the same in both cases, and I will call those currents I. Now, because this circuit is a very simple loop, I expect this current I will be the same everywhere through this circuit. So I should have the same current I flowing through the 3 resistors as I do for the equivalent resistor. The current flowing through each resistor must be the same because we don't want to have charge building up at any one location in either circuit. Because we have resistors with some current flowing through them, there will be a voltage drop across each resistor. Because we are told the voltage drop from points A to B must be the same as the voltage of the battery, I could say that the voltage drop across the equivalent resistor is going to be equal to V, which I could write as I times R equivalent from Ohm's law. Now there will also be a voltage drop across these 3 individual resistors, which I will label voltage drop across resistor 1 is V1, voltage drop across resistor 2 is V2, and voltage drop across resistor 3 is V3. I could also use Ohm's law to say that the voltage drop across resistor number 1 must be equal to I times R1, the voltage drop across resistor 2 must be I times R2, and the voltage drop across resistor 3 must be I times R3. In the circuit on the left, there are 3 resistors between points A and B, so there will be 3 contributions to the total voltage drop between points A and B. Those 3 contributions will be V1, V2, and V3. In the circuit on the right, there is only 1 resistor between points A and B, so there will only be 1 contribution to the voltage drop between points A and B, and that is V. Because the voltage drop between points A and B must be the same for both circuits, I could write that V1 plus V2 plus V3 must be equal to V. Using the relations from Ohm's law, we could write I times R1 plus I times R2 plus I times R3 is equal to I times R equivalent for our resistors in series. And then I could factor out the current on the left-hand side and write this as I times R1 plus R2 plus R3. On the right-hand side, I'll still have I times R equivalent. And then when I cross out the current on both sides, I am left with the claim that we originally made for resistors in series. We will now consider 3 resistors in parallel whose behavior is identical to a single equivalent resistor whose resistance is described by this equation. Just like before, we will consider 3 resistors in parallel, but this derivation could be straightforwardly extended to any number of resistors in parallel. Also, just like before, we will consider 2 circuits. In one circuit, we have 3 resistors in parallel that are connected to a battery of voltage V. And in the other circuit, we will have a single equivalent resistor that is connected to a battery of the same voltage V. Because we require that the behavior of the 3 resistors in parallel be identical to the behavior of the single equivalent resistor, that again means that if we were to imagine that we covered up the resistors in these 2 circuits, there should be no possible way you can know which circuit contains the 3 resistors in parallel and which circuit contains the single equivalent resistor. The behavior of everything going on in the circuits must be identical away from these resistors. Specifically, the current flowing through the batteries in these 2 circuits must be identical. If I look at the circuit on the right, I see a single battery and a single resistor in a loop. That implies that the current that flows through the battery will be the same as the current that flows through our equivalent. If I look at the circuit on the left, I have current that will flow from the battery, but then that current will reach a junction. That current will be split, and some of that current will flow through resistor R1, some of that current will flow through resistor R2, and some of that current will flow through resistor R3. and then those currents will recombine and flow back into the battery. I will label the current that flows through resistor R1, I1. I will label the current that flows through resistor R2, I2, and I'll label the current that flows through resistor 3, I3. Because the total current entering a junction must be equal to the total current exiting that junction, I can look at this junction and see that current I is flowing into the junction and currents I1, I2, and I3 are flowing out of the junction. Therefore, I could write that I is equal to I1 plus I2 plus I3. If I were to look at the other junction in this circuit, I would see that currents I1, I2, and I3 are all flowing into the junction, and current I is exiting the junction, so I would get the same equation. Now we will consider the voltage drop across the resistors in these circuits. If I look at the circuit on the right, the voltage drop across our equivalent is going to be the same as the voltage of the battery, so I'm going to call this voltage drop V. We will now claim that the voltage drop across each resistor in parallel will be the same, and that voltage drop will be the same as the voltage of the battery. So in other words, there will be a voltage drop of V across resistor R1, there will be a voltage drop of V across resistor R2, and there will be a voltage drop of V across resistor R3. Pause the video and see if you could come up with a reason of how we might be able to justify this claim. To justify this claim, let's temporarily consider only resistor number 1. We will temporarily ignore resistors 2 and 3. If I look at resistor 1, I could notice that the left side of resistor 1 is directly connected to the positive terminal of the battery, and the right side of resistor 1 is directly connected to the negative terminal of the battery. When I say directly connected, you could imagine that it would be possible to begin at the positive terminal of the battery, walk along the wires, and reach the left side of resistor 1 without having to cross over any circuit elements. And similarly, it would be possible to begin on the right side of resistor 1 and walk along the wires and reach the negative terminal of the battery without having to cross over any circuit elements. Now recall that we defined a battery as any device that maintains a constant potential difference between its two terminals. Also recall that the voltage drop along a section of wire is always going to be 0. So I could say the voltage drop from this location to this location, right nearby the terminals, must be the same as the voltage drop from this location to this location, because there must be 0 voltage drop if we only are moving along a wire to connect those 2 points. The voltage drop from here to here must be 0 because we only traveled along a wire. And the voltage drop from here to here must also be 0 because along this segment we are only traveling along a wire. Therefore, the voltage drop across resistor number 1 must be equal to the voltage of the battery. Now let's consider resistor number 2 only, and we will temporarily ignore resistors 1 and 3. I look at this circuit and I notice that the positive terminal of the battery is directly connected to the left side of resistor number 2, and the right side of resistor number 2 is directly connected to the negative terminal of the battery. Using the exact same arguments that we used previously, I could say that the voltage drop across resistor number 2 must also be equal to the voltage of the battery. And similarly, the voltage drop across resistor number 3 must also be equal to the voltage of the battery. Using Ohm's law, we could write that the voltage drop over resistor number 1 is given as V is equal to I1 times R1, where the voltage drop over resistor 1 is the same as the voltage of the battery. I could rearrange this equation to read I1 is equal to V over R1. Similarly, I could write I2 is equal to V over R2. I could write I3 is equal to V over R3. And if I look at the circuit on the right, I could say I is equal to V over R equivalent for my resistors that are in parallel. If I take these 4 terms for these 4 different currents and plug them into this equation here, I then find that this equation would become V over R equivalent is equal to V over R1 plus V over R2 plus V over R3. I could cancel out the V's in the numerators, and what I'm left with is the relationship between the resistance of the resistors in parallel and the resistance of the equivalent resistor.